So today we're gonna start with our chapter one revision on measurement, but we only touch upon two things here, which is the base quantity and the derived quantity. So I think this topics is gonna be important because it's related to the other topics that we're gonna learn later, especially force and motion, which already we learned that there consists a lot of physical quantities that require us the understanding of the units is how the unit become like that. And also for the topic on gravitation also involve a very difficult and complicated units as well. So in this chapter is basically tells us the fundamental, the foundation of the physics itself, because the physics depends on the measurement and thus is involved units. So let's start with our first concept here, physical quantity. So what is physical quantity? So physical quantity is a quantity that can be measured. So such as length, mass, weight, volume, area, etc., etc. How about a quantity that cannot be measured? We call it physical quality. Physical quality. So basically, cannot be measured. Objectively. But it means that it can be subjective, such as beauty, or intelligence, or the brightness of the face, for example, the fairness, the smoothness, or something like that. It cannot be measured. So basically what we need to focus is the physical quantity. So a physical quantity consists of magnitude plus unit. Okay, for example, the magnitude gonna be 20 and the unit gonna be centimeter. So that's the meaning between magnitude and unit. So that's physical quantity, something that can be measured using instruments such as ruler, triple beam balance, spring balance, measuring cylinder, etc. Okay, so let's move on to our first concept, base quantity. Base quantities. Basically, it means that quantity that cannot be derived from other quantities. So this is the fundamental quantities, the basic quantities. So what are the example of the base quantities? So basically we have length with symbol L. The unit is meter. The symbol is small m. Then we have, this is A, B, mass. The symbol is small m. The unit is kilogram. The symbol is kg. So the unit here is the SI unit. So SI unit means standard international. It means it's agreeable internationally. So in case you want to talk about science, you have to talk in terms of SI unit. So C after mass is temperature. So in our new textbook, our new syllabus is defined as thermodynamic temperature. So the symbol is big T. The unit is Kelvin. Symbol is big K. Okay. D, electric current. The symbol is bit I. The unit is ampere. Bit A. E, quantity of substance. The symbol is small n. The unit is mole. The symbol is MOL. Okay, let's make that clear. MOL. Okay, MOL. F time. The unit is small t. The symbol is small t. The unit is second. Small s, the symbol. G, luminous intensity. Luminous intensity. So the symbol is I nu. I nu. It looks like V, but it's actually a Greek symbol that looks like V, but it's slightly curved. So we call it I nu. It's sub. It's a smaller letter inside the big letter. The unit is candela. The symbol is C. So how many we have? 1, 2, 3, 4, 5, 6, 7. So we have 7 base quantities. So that means the other quantities that is not mentioned, that are not mentioned here, gonna be in terms of these 7 quantities. Gonna be defined in terms of these 7 quantities. Okay. So let's move on to derived quantity. Derived quantities. Quantity that can be derived, from other quantities. So how we can derive other derived quantities? We're using addition, subtraction, or multiplication, division. But usually just multiplication and division is going to be compound units. So for example, the easier one that we can derive here is area. The symbol is BA. So the formula gonna be length times length. So it's gonna be the unit. This is in terms of base quantity. So the unit is gonna be base SI units as well. So meters times meters. So we know that from mathematics, it's become meter square. Okay. So next, we look at volume. The symbol is big V. Is equal to, the formula is L times L times L. So in terms of base SI units, M meters times meters times meters. So it's basically meter cube. Okay, after volume, we learn about density. The symbol is rho. It's a little weird P, but it's slightly curved P. It's also a Greek symbol, rho. So the formula is mass over volume, but also we can make it in terms of like this: mass over length times length times length. So it will become, in terms of base SI unit, kilogram over meters times meters times meters. Or we can make it look like this: kilogram meter cube. So if we want to make it in a single line, then it will become kilogram meter negative 3. Okay, because the power 3 here is in the denominator, basically is in division rule. So you have to use the index rule here, make it negative. Okay, what else? So we already learned about Work done. Then work done. Or not work done. Before work done, before we go to work done, let's define something more simple than that, which is motion, the quantity of motion, velocity. So it's v, small v. The symbol, the formula is displacement over time or length over time. So length is m, meter, time is second. So if you want to make it in single line, it becomes meter per second or meter ms negative 1. Next is acceleration. Small a, the formula is v minus u over t, but in this case, v and u are the same unit. If we have the same unit, then we can add or subtract. Okay, that is the rule for addition and subtraction. You only can add and subtract if you have the same unit, such as this term over here. V is the final velocity, ms negative 1, and u is the initial velocity, also ms negative 1. Thus, we can add or subtract. But for multiplication and division, you can freely do that, even though the unit is different. So it's a little bit less stricter than addition or subtraction. So in this case, we just ignore the minus sign. It just becomes ms negative 1 over s. So since we know that we already derived the velocity in terms of the base unit, so but we can back up a little bit more. We can back up as the acceleration itself consists of length over time over time. So basically length over time square. Then we can define it in terms of base SI unit. Length is meter, time square is s second square. So if you want to make it in one single line, ms negative 2. So this is more appropriate in this case, but you can also do it like this. Over s, it becomes ms negative 2 as well. So no problem, but this one is more fundamental. We define it in terms of base quantity, not in terms of derived quantity, other derived quantity. So let's move on to the next concept, momentum. So momentum is small p. The formula is m times velocity, mass times velocity. So if you want to define it in terms of SI unit, base quantity, sorry. So m times length over time. So ml over p. Then we can convert that into base SI unit. Mass is kilogram, length is meter, time is second. So if you want to rewrite it in one line, it becomes kilogram ms negative. Or it can also be like this, ms negative 1 times ms negative 1, it becomes kilogram ms negative 1 as well. So this is a very simple one, but this is more appropriate way to do this, to define momentum in terms of base quantity. So after momentum, we will learn about force. So basically force, big F, the formula is mass times acceleration. So mass times length over time square, square. So it will become ml p square. So kilogram ms square. So if you want to rewrite it in single line, kilogram ms negative 2. Okay. So let's define other derived quantities. After force, we learn about impulse. The symbol is big J. The formula is mv minus mu, or m if the mass is not gonna be changed, so it constant, so we can factorize mass v minus u. So either way, or is also equal to f times t, force times time. So let's do this first. If we derive the units from this first formula, mass times velocity basically. So mass times L over T. So it will become ml over T. So if you convert that into SI unit, kilogram meter per second. So kilogram ms negative 1. So how about this one? So if you want to define that, force is ma times T. So if we want to rewrite it in terms of base quantity, it becomes mass times length over time square times time. So if you rewrite it, mLT over T square. Then we can cancel the T, only left with ml over T, which is this, the same as this one. Okay, so after impulse, we learn about impulsive force. So F equal to mv minus mu over T. Or if we can factorize mass, v minus u over T, so it will become ma. Yes, because v minus u over T is a, so it becomes ma. So basically this is equal to kg ms negative 2, or Newton. We give it Newton, the unit of Newton. Newton for force. As same as F equal to ma is also Newton for the units. So next we'll define work done. Symbol is big W. Is as force time displacement, force time distance. So if we want to define force, it become like this, ma times s. So if we want to rewrite it in terms of base quantities, it become m L over T square times L. So S is still L. So rewrite it ml square over T square. So we can do it in terms of base SI unit, kilogram meter square over S square. So it becomes kilogram meter square S negative 2. So we give this whole thing here the unit of joule. Joule. What kilogram m square S negative 2. Power. Big P is equal to work done over time. Fs over time. So S over time become Fv, velocity. So ma times v m L T square times L over T m L square T cube kilogram meter square S cube, or kilogram m square S negative 3. So we give these whole things here the meanings of watt for power. Okay, so it looks like a very complicated, but it's easier if you understand the formula. Okay, let's do some a little bit more. What else the quantity that we can do? We can define power for electric current. So power for electric current. So it's still P equal to voltage times current. So voltage has the unit of volt. So I make it look like this, volt. The current has a unit of ampere. So it's just like that. But if you know the basic things about volt, so let's do it like this. Voltage is actually charge, the amount of charge, the amount of work done over charge. Work done over charge. Charge is Q. And then before we define charge, and before we do this, we need to define charge as well. Charge is Q equal to current times time. Okay. So in this case, we can define charge because both of the units are in base quantity already. So it becomes ampere second. And then we can go back here. Work done is Fs over IP. So we see the S over T here. So it becomes F over I, B, FB over I. And then F, MAV over I. And then we can then derive in terms of the quantities of T square, or not kg yet. It's still M. L T square, L over T over I is I. I is I. I is still I, because I is the base quantity. So simplify that terms. PQ over I become ML square I P Q. Then we can define it in terms of base quantities, in terms of SI unit, kilogram M square ampere S cube. So this is the definition of voltage. Volt. Then we can rewrite the above, volt times amperes, kilogram M square over AS cube times A, which is the A can cancel out. It becomes kilogram M square over S cube, or kilogram M square S negative 3, which is we already defined it as what? Before, same as before. So we basically, this formula here is correct. What we learned during Form 3 is correct. So what else that we can do here? Power, voltage, charge, acceleration, weight. Let's define weight. Weight is W equal to mg. Basically, it's just acceleration. So ml over t square. So it becomes ml over t square, or kilogram ms negative 2, kilogram ms negative 2, which is Newton. We already defined that as Newton. Pressure, BP equal to F over A, force over area. So force is MA over A. So we can define M L T square over L times L. So simplify that. ML T square over L square. So ML L square T square. Then we can cancel out ML T square. So kilogram meter S square. So kilogram M negative 1 S negative 2. 2. So this is the unit of Pascal. We define it for Pascal precision. Kilogram m-1 as -2. So what else that we can do? Pressure, power, charge, weight. Let's do for the Newton's universal law of gravitation that we already learned. We derive the unit of G, the constant G. So for Newton's universal law of gravitation, Fg equal to big G, big M, small m, r squared. So we want to define the unit for G here. So let's rearrange Fg r squared over big M, small m. So rewrite it in formula r squared over m and big small m. So basically we can cancel out m. It become a r squared over m, and then a, let's see, we can cancel m. So let's back up first. Yeah, I think we can cancel m. Yeah. So m r squared m, then we can cancel out m, a r squared over m. So L T square, L square, because R is the distance, kilogram, L cube over T square, kilogram. Oh, not kilogram, still M here. Still M. So it becomes L cube T square M, meter cube, kilogram S square. So m cube kilogram S -2. Let's see, this is a little bit weird. So let's erase it first. It should have m square, not m cube. So we might be wrong somewhere. So let's back up. G. Yeah. I think it's correct. That's correct. Yes. So L cube over T square over M. So L cube m T square. So m cube kilogram S square, or m cube kilogram -1 S -2. So this is the unit for the gravitational constant, the base unit. But we know that we learn it become look like this. It's supposed to look like this. How come it's not look like this? Because this Newton over here is actually a derived unit. So it's not a base unit. So we can redo here. If we want to redo, this become Newton. This is meter square. Below is kilogram square. So it become an m square kilogram -2. So how about if we replace Newton with kilogram, ms -2, m square over kilogram square, does it become m cube kilogram -1 s -1 or not? So let's check. We can cancel kilogram and kilogram here. M here are m cube s -2 over kilogram. So basically, it become m cube kilogram -1 s -2, which is equal to 0. So our formula is correct. So I think that's all for today. Hopefully that you know how to derive physical quantities given the formula. Make sure that you define the formula to a more simpler terms into a base quantities before you turn it into base SI unit. But if the SI unit also have a different version such as Newton, Pascal, Joule, Watt, what else? Volt or Coulomb or other whatever that has already standard unit, then you can also directly apply that as well. You don't need to make it in terms of base units solely. So I think that's all for today. Hopefully that we can continue on our revision soon. Thank you.